elements of a space when you talk of it. Really, space here means about 100 kilometers, up to 100 kilometers, you can assume that this is atmosphere. That atmosphere, of course, thins very much by the time we go to 100 kilometers, even thinning further. But above 100 kilometers, you call it a space. And this space has got high vacuum because of the fact that the atmosphere is very rare there, very rarefied. Then you have got a lot of radiation that comes from the outer space, like the charged particles, electrons, protons. The solar radiation comes in. Then there are other types of radiation like ultraviolet and those kind of things. So there are very lethal radiation that pervade the space. The third thing is the space is extraordinarily cold. Actually, the temperature of the space is what you call as 2.7 degrees Kelvin. It's really the coldest that one can experience. So if you look at all these kind of a thing, you are really talking of a very hostile environment. And if you want to put an object, a man-made object into that thing, you need to have a high degree of ability for it to function under this hostile environment with reliability, with the confidence that it can function. So these are the challenges of a technology that we need to do. So you need to build satellites which can be then used by orbiting it around the Earth. What happens when you try to acquire space? What it means by acquiring space or try to get vantage point of space, putting an object there means you have to escape from the gravity of the Earth, but still use the gravity of Earth, go around. It's almost like what you call the centripetal force, centrifugal force. Many of you youngsters would have learned in your classes. So this is a balance between the centripetal and centrifugal forces. If you take a stone and then put it on a string and then move it, you can feel that force on your hand. It's exactly what happens when the satellite moves around the Earth. And though these kind of satellites then becomes a very useful tool to look at the Earth, look away from the Earth, and that becomes a very potential means of doing quite a lot of things, some of which we will see now. But then building a satellite is a lot of engineering, and this university, of course, has very good important courses on engineering. And so I may say that this is an interdisciplinary product, a satellite. It has structural engineering, thermal engineering, communication engineering, digital electronics, electro-optical system, electromagnetics, and control and guidance, and so on and so forth. So there are a number of engineering disciplines that have to come together, and they have to be put together in the form of a functioning system, a product, and that which you call a satellite. So in order to understand this kind of a thing, you need to have teams which work in several areas, but they are able to bring together all their expertise to make sure that you have an ultimate product, which is the product of all these engineering disciplines working together and interrelating to each other. So that's what we wanted to initially must, and then it has to go and function in the hostile environment of space. That is where the Aryabhatta idea was born. The first of the satellite we wanted to build was even smaller than that. About 40 kilometers, what we called as Rohini, was the one that we wanted to build to get master of this various art of building a satellite. But in the meanwhile, those were the years when India was very close to the then Soviet Union. And the Soviet Union wanted to help India in the space program in those years. What I mean is something like 60s. So the ambassador of the Soviet Union called Dr. Vikram Sarabhai, and he asked him, why don't we work together in building India's first satellite? And then Sarabhai said, yes, we could do that. And then Sarabhai explained outside, no, it should be much bigger than that. He asked Dr. Vikram Sarabhai, what is the weight of the first Chinese satellite, he asked. And Dr. Sarabhai said it's about 160 kilograms or so. At least make sure that the first Indian satellite is heavier than that. So that is the criterion that the ambassador said, and we will build that. So that was the genesis of Aryabhatta. The Aryabhatta was to learn the method of building a satellite, a multidisciplinary product to work in the environments of the hostile space. And then there was its collaboration with the Chinese. By the time Soviets had already done quite a number of satellites, so they knew precisely the art of making this. We jointly built together. But it's also what is interesting is that we wanted to also not just try only prove the technology alone. Use this opportunity to go and outer the space and try to do some scientific experiments. So we put also 3 scientific experiments into it to look at the sun, to look at the radiations coming from outside, and also to look at the satellite environment, because even at those altitudes of 300, 400 kilometers, there is a residual atmosphere, but what you call as an ionosphere is ionized atmosphere. So you could look at all those kind of a thing. So that was the objective that was put as scientific, but more important is to study the method of making this particular satellite. What I would like to convey is this was a very tall order to do it in 30 months, because that is all the government gave. At that time, Madam Indira Gandhi was the Prime Minister, and he said we need to do it in the next 2.5 years. We didn't have the right number of people, we didn't have the experience of building this, we had to create infrastructure. So this entire gamut of things was done over the matter of 30 months. And by 36 months, that is within 3 years from the point of conception to the delivery and launching, we achieved it in the 36 months. It's considered as a kind of a record for a kind of background in which we are. We don't have that kind of an industrial support for this, the design support, the expertise and the infrastructure. But in spite of all these hurdles, we could put together a team of youngsters, many of you are your age here, and that they could build this satellite itself was the most creditable experience that we had. And that was the first story, that of Aryabhat. And then we having built the satellite, and we wanted to know now what will be used for. Sarabhai had been saying that it will be used for education, it could be used for communication, it could be looking at natural resources survey. So first thing we decided is that we will try to adopt this satellite. We were working with the Russians, and the Russians always take care by saying that you should build a standby model, and in case the first thing happens, something goes wrong with the first, then you should go to the next one. So we had a standby model. So we built a standby model. But we thought that how do we use it? The whole interest then was how to look at the natural resources of the earth. What you try to do is you put a camera in the satellite, take a picture from that altitude of 500 or 600 kilometers. You can have a very perspective view, because I stand on a higher level here, I can see the whole hall. If I come down, I can see a limited hall. So the whole idea is to get a perspective view of the ground by taking a camera picture from the space. So that is what we wanted to do. That is called as a remote sensing satellite. It's a very rudimentary system we thought of with 1 kilometer kind of a resolution, which can see broad features like river systems, geological features, large forest trees or delta systems of rivers and so on. But you can't go into the nitty-gritty details of buildings or those kind of a thing. But we thought that we should get our hands. And that was the genesis of Bhaskara. I have only one interesting episode about Bhaskara that I would like to convey, because that's a very challenging and interesting experience. We built this camera, and this camera was to be flown in space, and space, as I told you, is a lot of vacuum, very limited atmosphere. And when we had to do this, camera had a high voltage system. And this high voltage system, as you know, that if you don't take care in operating it under various conditions, especially the atmospheric condition, it can arc. You would have seen this in rainy season, sometimes some of those transmission lines arcing. This is all because of the high voltage arcs with the atmosphere, and then it ionizes at that particular point, and you have a arcing system. Something like that was expected in this kind of thing, we had to test it. After testing it, when it was flown, even though we had tested it for 14 days, after when we switched on the camera after 3 weeks, we found that there was a heavy arcing. The satellite was getting highly disturbed. We went into this, we had a standby system, we put that instrument into that standard system, standby system, and started finding out what exactly has gone wrong. And it was arcing, so we could operate the camera. And then we found that there was at a particular point, there were occluded gases. So the gas provided a path to arc, and therefore a high voltage system was connecting, and it was giving. But engineers didn't give it up. They said that we should try to find we should get to the bottom of this problem. And then when they did more and more simulations, more and more modeling, they did also laboratory evaluation, like in space simulation chamber, which you see there. They came to the conclusion that there's a good possibility that this gas can come out, and then ultimately the camera can come out. The problem is, whereas if something goes wrong here, you can immediately fix it. When it is in space, you don't have any means of accessing it, except for a radio wave by which you can control it to some extent. So this was evaluated, and then we told the then chairman, Satish Dhawan, that there is a good chance that we should be able to recover. And he said that, okay, go ahead, I am not very confident that we are going to get this thing on order. But then finally what happened is, that after 6 months, the youngster predicted that it will happen. We switched it on, and here was, lo and behold, the first images of this country coming from space. There was a setback. We tried to understand the setback. In the process of understanding the setback, we had this solution, and this solution helped us to recover back what was called as a failure of a mission, and we got the mission back. So this is a lesson that we learned, that these are kind of things on which best scientific talent, the best of the argument, the best of simulation, these kind of things are behind this. Today is becoming an order of the day. So this is an example of that right in the early phase of the space program. Similarly, we built another satellite. Primarily, this is for remote sensing for using for communication and broadcasting, and that is called the Apple and Ariane passenger payload experiment. Again, all satellite technology. But the interesting part of this is, whereas we can put this satellite about 500 kilometers, the Bhaskara, we need to put it at 36,000 kilometers, because at 36,000 kilometers, if you put a satellite, it has got a revolution period of 24 hours. The rotation period is 24 hours, so you find that that particular point remains stationary. So it becomes a tall tower, and when you have a tall tower like your television tower with maybe 50 or 100 meters, here is a tall tower of 36,000 kilometers, you can see 1/3 of the Earth. So you can see its potential as a tall tower for communication and television broadcasting. So that's the idea of building that particular satellite. We built that too. So we mastered satellite technology. We mastered the method of building a satellite along with a camera system for taking the imageries of the Earth. We built another satellite by which you can do communication. So all these, in the matter of something like 15-20 years, we mastered the entire art. Then we went into operational system. This was only study phase, evaluation phase, familiarization phase. From this we went to the operational system. Today we have INSAT systems. The INSAT systems today provide communication. It can provide broadcasting. It can provide meteorology. One of the interesting aspects of locating at 36,000 kilometers with a camera is you can look at the meteorological phenomena. Similarly, you can also have it for national satellite navigation, for position fixing. Then ultimately also we build the world's best satellites for remote sensing. I should say particularly for remote sensing. The remote sensing is also used for prying the adversaries. So this is not a technology that is easily accessible to many countries. So India was probably the third country to embark on a remote sensing satellite of the sophistication that we wanted, after United States and France. We had to build the camera system. We had to build the platform of the satellite has to be extremely stable if you have to take good pictures of the ground. And this satellite will be hoisted at something like 900 kilometers. And this camera should be sensitive enough to look at vegetation and things of that kind. It is like taking a picture from Jaipur for a coconut plant which is located in Delhi. So you can see the type of power that the camera needs. So that is what was done for this kind of a thing. We again embarked on it with no information, right from first principles. We worked on, in a matter of 6 years, we built the satellite which was comparable to the contemporary satellite that the French and the Americans made. And this used camera systems, it used a variety of satellite technologies, and especially the stabilization system to look at the Earth. And some of the pictures that they returned were the most beautiful, and most importantly, we got to the point where Americans and French were there, right in the 1980s. And then somebody said that we can even go further, and then we built the world's best remote sensing satellites, which became a kind of a path-breaking system for the whole world to see. So in fact, it was again a challenge by some of the youngster engineers who said that if we can build satellites like what Americans and French have built, why can't we build satellites which Americans will say, why can't we build a satellite like what Indians have built? That is what we achieved in the next generation satellite system. This is the story of these particular 3 satellites, and I'm just giving you a type of a picture that is taken by the Indian satellite. This is a part of the UAE, they are developing those lamps, and you can see the beautiful picture that the IRS has returned from that location. It can take pictures all over the globe, so you have this kind of a thing. You can see a camera system from INSAT from 36,000 kilometers. This is a picture of the Philly cyclone. Which was October 2000. You can see how well this can be tracked, and you can also see where exactly it will hit the coast. And these predictions now are made. We also have this kind of information, and also about the atmosphere. You can really predict where exactly a cyclone can hit the coast. This is another kind of an application. So just to summarize how our satellites are doing, you can see. You can use it, the remote sensing satellites can use it for agriculture, education, land, forest. Several of these resources today, timely information, accurate information, precise information in all these areas today are possible with the remote sensing satellites, and with the communication satellite, we can use it in broadcasting. Something like 200, about 1,600 channels today are provided by the INSAT system. You can see Doordarshan and many other television channels, they're all coming out of the INSAT. You have also broadcast communication system. It is also used for tele-education, something of interest. I am sure that the JKLU is already using these kind of tele-education methods to connect with the best education centers all over the world. This is something that was used. We only promoted a satellite exclusively meant for education, the EduSat, coming out of the principles of communication, secure communication, rural communication. There are many things to which it is applied, and also using the synergy to look at a particular area which could be probably a disaster prone, and a synergy to look at communication we can also bring in as an effective tool for disaster management. This has been done for flooding, it can be looked for drought affected zone, it can also look at earthquake affected zone. So there is a whole host of things which can be done with this kind of a system. I come to the other interesting aspect. You know, when you go above the atmosphere, you have an unimpeded view of the universe. When you stand here below on the Earth's surface with the blanketing effect of the atmosphere, it protects you, of course, in terms of ultraviolet radiation, which can directly otherwise come. It also regulates the temperature of the Earth. Otherwise, the greenhouse effect and the climate change that we are talking for, this would have been not there if the atmosphere was not present. But then the atmosphere is really a protective mechanism for nurturing life on the Earth. But at the same time, it becomes an impediment for the entire electromagnetic spectrum to be seen from the ground. So you need to go up. So in order to take advantage of that, you build satellites to look at, say, how does the universe look like in the X-ray region? How does the universe look like in the infrared region? How does it look like in the radio region and millimeter region? So that is where the satellites are used for looking at astronomical observations of stars, galaxies, even multiple galaxies, and also the fringes of universe, how it is been, and to understand evolution of stars, how does evolution and ultimately how does the star end its life, or how does a galaxy formation takes place, and things of that kind. So one of the satellites that we are building right now is an AstroSat, which is again an offshoot of the astronomy interest in this country. And this satellite will really investigate the universe in its manifestations like neutron stars, black holes, stellar explosions, galactic structure, and things of that kind. And another satellite which we are building is Aditya, a satellite to look at the sun. Because the sun has a lot of energy, ultimately we get all the energy from the sun. And the question of a sun-weather relationship now is becoming an important area of science. So we should understand the sun in its behavior because it influences the life on the earth. We are building a satellite which will be able to be located maybe several thousand kilometers away at a location from which you can continuously monitor the sun, what you call the corona of the sun, the outer radiant area, by blocking the main photosphere. This is called as a coronagraph. This we are right now building. I come to another area which is related to the ability of accessing the space, means ability of accessing the ability to put a satellite in space. You need what you call the launch vehicle. We build these satellites, and these satellites are ready. There is always a possibility that because the satellite can be used for several other purposes, including national security or for defense, you may not get people who can launch it for you. So it is necessary right in the beginning of the space program. Sarabhai decided that we should have the ability to access the space, and that is where the launch vehicle has come. Over the last 30, 35 years or 40 years, we have gradually built up this capability, right from sounding rockets to the first SLV at 40 kilograms, to the PSLV at 150 kilograms, to ASLV to PSLV, which today is a workhorse, putting multi-ton satellites into near-Earth orbit, and also having developed the GSLV, which is the ability to put the geosynchronous, because you know these satellites that we hoisted at 36,000 kilometers. Typically, they are 4 to 5 tons in weight compared to the remote sensing, which will be 1 to 2 tons in weight. So you need much powerful launchers. That is what the GSLV Mark 1 we have successfully proved. More recently, with 1 point here means upper stage, which is a cryogenic. I don't want to go into the technical details of this, but it's a very, very advanced technology of low temperatures, materials, problems of turbo pumps and things of that kind. So that particular problem has been now solved. We have an indigenous cryo stage also, which was flown very recently. So we are right, except for the last launch vehicle, which is a multi-ton launch, very ambitious program, which will happen in the next 2 to 3 years. We have mastered the entire technology of putting the satellite. It's one of the most difficult technology. Hardly 4 to 5 countries in the world have mastered this at the level at which today we are where we are. And so this is a technology which encompasses several critical areas, technology for aerodynamics, in terms of atmospheric flights, in terms of control, guidance and navigation, propulsion. I can keep telling you some of these are all high-level technology. Really, when you prove a vehicle like this, what it signals to the world is where we are right in the front, right at the frontier. So that's what we've done. And of course, now we are in the process of developing the next vehicle. But just to give you a flavor of what does a launch look like, I've just put in a very small this thing here, video here. This is the launch of our first GSLV flight in 2003. And this flight was the most important flight in terms of establishing India's credentials to launch vehicles which can put geosynchronous things. So you can see it has now gone up. Then it will slowly start separating out the various stages because you try to optimize the flight. So you have this various interesting flight. So you can see that then the first stage will separate, and so after the first stage separates, then you have, the separation is now being shown. This is now animated, and because we can't take the picture at this level, and then another interface ring is separated. The second stage will, but the heat shield, it protects the satellite from the atmospheric flight because it really doesn't create friction in the way the friction of the atmosphere in the fast flight really heats up the satellite. That is done, and now last phase of the flight, which is the cryogenic stage, and now at this stage it gets the necessary velocity to be released. Now it is free in the orbit. So this is a very interesting thing to give you an idea of what it means to launch a satellite from the space. Another dimension of the space program has been the manned flight. We didn't have much to do in the early phase of this Indian space program. In fact, even there, the Soviet Union offered that whether they could help us to have a manned flight program. And they offered an astronaut or a cosmonaut from India to fly, and that is Rakesh Sharma, who was chosen as the first thing. He flew there. And the most important aspect of a manned flight is, right now it has become, how much is it useful, how much it can be used as like what you use it for remote sensing and communication, that is still being assessed in our country. So the question of having a launch flight is a very resource intensive. You need to build another kind of a space program which can be quite independent, and then we need to make sure that it has a utility. So when this proposal was offered to India, the then Chairman, Dr. Satish Dhawan, said that he's a very pragmatic person. He said that this kind of a thing, if we try to get, then we need to be able to sustain it. We should find a use for it. That is where there were some question marks. But nevertheless, the political system, both at Indira Gandhi's level as well as Brezhnev's level, they decided that we should go together and demonstrate India's interest in this program, which was not relevant at all in that context. But it was, Professor Satish Dhawan thought that it was too early, but nevertheless, he supported the whole program. I'm only pointing out this to show that how careful and how objective some of these people are in taking decisions which involves country's resources. So they went, Rakesh Sharma flew, it was a proud moment for Indians, and the famous words like when Madam Gandhi asked, Bharat kaise dikhte hain, sare jahan se acha, that the famous statement that you made, these are all part of the history. But now, of course, India is in the process of developing these kind of capability. The first steps are being taken. I will say a few words about it a little later. That took us to the planetary exploration. You have built remote sensing systems, you have built communication systems, you have now gone to the scientific satellites, but now what is the next step? That is where we thought that now we should go to the outreach well beyond the near Earth orbiting systems. And that is where can we go? The first target, of course, has to be Moon, simply because of the fact that it is the nearest object to the Earth, a celestial object, about 400,000 kilometers. So one can reach it, one can accomplish a mission with our own launch vehicle capability and satellite, on which we have developed quite a bit of capability in those times. That is about 2000, early 2000. So that is a way. But then you have to sell this kind of ideas to public. There is public money involved. There is always this question. Is it worthwhile to spend 200, 300 crores on a planetary mission which gives nothing to this country? So it has to be taken through a very logical route. And what I'm trying to tell you here is a way in which the entire decision-making process has been made transparent, accountable by giving it to several fora who could provide judgment about this kind of a mission, like presentation on a technology day. This was Pokhran 2 day, and where the first ideas were germinated, and there was a tremendous positive enthusiasm from the country when it was reported in the papers. And then there was the Academy of Sciences, people who really, the intellectuals who wanted to give a view on this particular thing, that was gone through. Then there was a national task force which went into the nitty-gritty detail of what such a lunar mission would mean. And then there was a review. Then it was taken up by the highest policy-making body, what you call the Space Commission, who decides the policies of this kind of a thing. And finally, presented to the then Prime Minister, the Prime Minister Vajpayee. Vajpayee only asked one thing: do we have really a clarity about the acceptance of this as a mission to India, for a mission, and for the kind of money that we are going to spend? So we explained the whole process of 4 years we have gone through before we brought it to the attention of Vajpayee. He said, तब तो करो एक पेपर दे दो मुझे next time August 15 आ रहा है I'll make an announcement for this country and so we made quickly the paper we made suggestion that it can be called as Somayana and so Somayana was the mission called for going to moon and then Bajpayee in 2003 August 15 announced it from the ramparts of the Red Fort that India is going to go into the planetary exploration era and this exploration era we are going to launch the first spacecraft to the moon and it will be called Chandrayaan 1. Obviously, he has changed from Somayana what we gave into Chandrayaan. So obviously, next day I went and asked him, how did we had given you Somayana? He said, I know, I also consulted some Sanskrit scholars. They felt that Chandrayaan is a better name than Somayana. And I said, we had only put Somayana, but you put Chandrayaan 1. One to main add kar diya kyunki how can a country like this have one mission for planet? We need a series, we need a program. So you can see the thinking. What I want to tell you, youngsters, is the system as a total, whether it's political, scientific, intellectuals, or other kinds of societal components, they're all, for whenever something good is going to happen to this country, they're all with you. And therefore, one should not be afraid of taking these kind of major decisions involving certain limited resources of this country. And the success of the Chandrayaan has proved that we are able to reach the moon, we are able to do scientific experiments on the moon, and water, which has been a big question mark so far as moon is concerned, was detected first by Chandrayaan. So you can imagine what kind of thing is there. And then we learned the whole art of going to another planetary body, which was totally a game shift so far as the capability of space is concerned. So this is all achieved through a process of very careful evaluation and so on. But then human mind is always restless and you'd like to go further. After all, I said from land to sky to space, humankind, when it goes to moon, then they will ask, why can't we go further? So that's the genesis of a Martian thing, the next one, which came as the Mars Orbiter mission. The Orbiter mission, the Mars mission, is really a mission to go to Mars and demonstrate that we can take a deep space exploration mission. And this exploration mission, of course, is crafted in a way, today, of course, it has traveled something like 190,000 kilometers it has already traveled. And it is totally traveled about 680 million kilometers. 680 million kilometers it has to travel. And it's got the radio distance. It takes a very circuitous path. It goes from Earth, it goes around the sun because it can get the gravity assist. The sun gives it a gravity kick, so it gets some extra energy. Then it moves towards the Mars, and now it is on the way to Mars, but under the influence of the solar gravity. It's no longer under the influence of the sun's gravity or the Earth's gravity. So it's traveling in the space, and it has now, so far, it has been functioning absolutely as per the requirements, as per least to the accuracy of a textbook precision. So that's where it has been. Now, what do we learn out of this kind of a mission? It's a long control, guidance and navigation, and it has to navigate in the space. It is exactly like if I were to put a cloth around your eyes and then you are asked to walk, what will you get as a feel for your orientation? This is the way in which the satellite is, the spacecraft is, and then it needs to have sensors. It looks at the stars, it finds out its own. At least when we drive on the ground, we know that there is a building here, so I should go through this road, and there is a turn there. But you don't have any such references there. So that's the beauty of this kind of planetary exploration. It has autonomous navigation system, and also when it's very far away, even the signal that comes from there takes its own time. Right now, at 16 million kilometers radio distance, it takes 2 minutes for the signal from that Martian explorer to come to Earth and then go back. So if you want to say hello, it takes another 2 minutes for the hello to reach back again. But then by the time it goes near the Mars, it could be as much as 20 minutes. So you can't correct everything that goes wrong with the Mangalyaan. So you need to make sure that there are automatic correction systems, artificial intelligence, and expert systems and so on. They're all built into it as a component of self-correction. If anything goes wrong, there are already, this is an enormous amount of computational capability, software, hardware elements. and of course the trajectory computations are some of the most demanding. These are the kind of challenges that the Mars orbiter mission provides. From here then one, the reason why we undertake all these, of course, I can see when you clap hands about Chandrayaan and Mangalyaan, it's very clear to us that there is a tremendous enthusiasm among the youngsters to be a part of this kind of mission. So there is what you call as igniting the minds. So that is one. The second thing is there are a lot of scientific, we have not even touched the tip of the iceberg on the scientific side. How did the moon evolve? How did the moon originate and how did the moon evolve? Whether life was there on the Mars, whether water is there on the Mars, these are question marks again. So there are all these kind of things that need to be taken up in the future. So this is number 2 reason. Third is we cannot afford to spend much more money than what we are spending now. So we need to be a part of an international community. And you have to be a part of the international community, you have to qualify yourself. So you create your own credentials. And that is what we are trying to do to show that we can reach there. And lastly also, the most important thing is that when you don't have that capability, when you have a capability but you don't use the capability to reach where you want to be, then tomorrow some of the more advanced countries may come within them and they'll create a law that the people who have not been able to go to these kind of things, they will be barred in future, like happened in the case of nuclear program. It could have happened in the Antarctic, but we were clever enough to go there and pitch our tent there. We have now pitched our tent with moon. We will be there on Mars. So there is no way India can be debarred from going ahead and carrying out space missions as a part of an international community when the future opens up. Now, what is the future that is going to open? And that's what I'm trying to see in the last but one slide here. You will have near-Earth missions. You will have missions where the people will be moving around the Earth. So there will be permanent presence of human beings in the near-Earth orbits. Then you can also use those permanent presence space stations to put crafts going towards various planets and asteroids and so on. That is one thing that is shown. So one way is to take manned missions, keep permanent presence of man, and from there do planetary exploration, asteroidal exploration and other things. On the other side, you also take from the Earth directly to the moon, and moon can be a launching pad for going further into the solar system. So there is going to be the human agenda for space is going to be ever widening. They are, of course, consistent with the exploratory spirit, the adventure spirit of the humankind. So we are going to be a part of it in the coming decades and coming centuries. The necessary base has been laid through these kind of missions, which itself has been very useful, very interesting, very challenging, and most importantly, scientifically worthwhile, and also by making sure that the youngsters will take interest. So we have moved from that stage. We will start slowly moving into this. This whole agenda can take 100 years, 200 years, but unless you have got a certain base, you can never reach that agenda, and that is what India is currently doing. So how do we look at it in the next 20-25 years? You can very clearly see that we are going to improve our capability to access space. Today, if you want to access space, it costs about $25,000 per kilogram to be put there. So you need to make it more cheaper, a better system of launching, recovery systems, reusable systems. These are all trying to do a better system for propulsion and so on. And then long duration spacecraft, servicing spacecrafts in orbit. Then manned mission capable of carrying out several, one of the interesting aspects of space, it also, and when you got a laboratory, a mission, object in space, a laboratory in space, it provides a microgravity environment because the gravity is very small. So there is something very interesting you can do. You can have protein crystal growth. It breaks when you have it on the full gravity on the ground. You can look at the medical aspects of it. When the astronauts go up, the blood circulation completely changes. They lose calcium bones, phosphorus in the bones, and so on and so forth. And then they have to orient themselves. But these are all interesting aspects of some problems which one sees in the Earth, for which the solutions can be simulated by looking at the cosmonauts' behavior or astronauts' behavior in space. So there were medical aspects of this. There are many other spin-off aspects of it. So the whole program is going towards better launching system, better space transportation system, better applications in agriculture and many other areas through remote sensing, better system for communication, broadcasting, including education, telehealth and things of that kind, and ultimately to be a part of an exploratory era, a planetary exploratory era, which will be an important component of the space research in the coming decade or so, or maybe coming century or so. So the necessary groundwork has been played, and most of you youngsters who are here, I am sure, will take full advantage of these capabilities and take it forward as you move into your own professional career. I conclude my talk with something, when first was Rakesh Sharma, I said, Kalpana Chawla was the Indian-born astronaut who flew Columbia first. And with the first Columbia flight, there was to be a communication to our Prime Minister when she was flying. And at that time, Mr. Indra Kumar Gujral was the Prime Minister, and he called me. I was the chairman of ISRO. He called me to his office, and he told that she is going to be flying and she's going to get a message. I'm going to talk to her. What is the kind of a thing? I will talk to her. Then I told him about Megha Sandesha, the Kalidasa, the swan looking at the Himalayas, giving a description of the Himalayas. And how one of our professors in remote sensing said, later on in satellite pictures, we looked at Kalidasa's imagination about Himalayas, not very different from what the satellite pictures showed about Himalayas. So I explained all these things. So do you see the same thing of Kalidasa's message in Megha Sandesha? You can ask that. But he had his own ideas. I think Indra Kumar Gujral was, he was an intellectual. So when actually he didn't tell me what he was going to say, but when they started dialoguing between Kalpana Chawla and him, he said, सितारों से आगे जहां और भी हैं अभी इश्क के इम्तिहान और भी है. This is Muhammad Iqbal. I have said it, Muhammad Iqbal, in the English version of it I have said so many, I don't want to read all of them, but I want to tell to the youngsters, why worry if you lost one abode? There are 1 million addresses to claim, and claim those 1 million addresses. That is what I would like to say. And all I can say is, I think the times are going to be extremely interesting, very challenging, and going to provide you excitement. I think the question is whether you're going to pick it up and take it. And India is certainly poised to move forward in spite of all of, we may have problems here and there, but I tell you the totality of the country is absolutely strong economically, and this is all very well exemplified by the adventurers, the pioneers in India's economy, industrialization like Singhanias, who have given the country a very special privilege of taking it to a level where we can claim to be really an economic power. And we are really talking of 7%, 8%, even though there may be small adjustments we made currently about the growth rate in GDP. Coming from Planning Commission and knowing a little bit about this, I have learned economics only very recently, very little that to minute. I can say with confidence, the 8 to 9% growth will be a reality in the coming decades, and certainly. And when you get that kind of a growth rate, India is going to actually by 2030 or 2031, India can be the third economic power besides the United States. And India is going to be the third economic power. There is nothing we can stop. And science and technology will be right at the forefront, is already moving in that direction. Catch it up and wish all of you the very best in using this capability. I am sure the success will be yours and India's glory. Thank you.